So thanks for this introduction. Thank you for being here. Thanks to the committee for having read my manuscript and for being here today so that we can discuss the use of probabilistic generative models for socially intelligent robots. My name is Xavier Alameda-Pineda, and I'm a researcher here at INRIA in Grenoble. So this is not working for some reason. It was working this morning. Yes, it's working now. So social intelligence is the ability that we humans have to understand what's going on around us in terms of social interactions, to engage into them, to adapt if they evolve, and of course to disengage when necessary. You can see here in the video, let's say, so-called social robot that is supposed to be interacting with that person that is approaching it. You can take a look to the video in YouTube and you will easily understand that the robot has absolutely no clue on what's going on. This has two consequences. The first one is that at some point an engineer has to step in to reboot and reset the robot. But the second consequence, which is a bit more important, is that the person that is interacting with the robot is adapting his behavior, and it looks almost like at the end of the DVD that the person is looking at the robot as if it was a kid. So now imagine what would happen if you put this very same robot in environments such as the ones that you have in this slide, in which there's many people, they are talking to each other, maybe looking at the smartphone, reading a book, checking some things with the front desk, or going to the restroom. And here the robot needs to navigate in the physical sense, but also in the social sense. So the robot needs some kind of social intelligence, meaning the capacity to look, to understand what's going on, and also to react to the environment and to take action. And more importantly, it needs to adapt to the user so that the user doesn't need to adapt to the system or to the robot all the time. I have identified and listed here a few challenges that we can find in these kind of scenarios. The first one is that we humans communicate mainly in a multimodal way using audio and video. The environment in which we are, because we are social animals, are severely populated with many persons, and therefore we need to understand who said what and who did what. The third challenge that we're facing is that the link between who did what and who said what and the raw signals that are actually collected by the robot sensors, meaning the images and the waveforms, this link is very complicated. So we need smart methods to actually exploit it. On top of that, when the robot goes into a new environment, we have very or no annotated data into this new environment. So therefore, we need to adapt in these conditions of data scarcity. Luckily for us, the robot can take action, and therefore it could use these actions to enhance the perception to enhance its own perception. However, the actions need also to be socially acceptable, so we need to take care that these actions satisfy let's say, the social rules of conduct that we have between humans. And if this was not enough, on top of this, we need to take into account that the computational resources of the robot are quite limited. So in the following, I'll present 3 contributions that will be dealing with part of these challenges, and we can discuss these other challenges that I shadowed down here as part of the future work or the conclusions. So the contributions that I will present are all based on probabilistic models with latent variables. So this is our methodological backbone, in which we are going to try to learn a set of parameters theta that better represent the observed data X. Sorry, there was some noise. As I said before, we want to have a link between what the people say, which is latent for us, it's unseen, unheard, and what we are actually hearing and seeing. So these latent variables will be denoted by Z. And once we have learned the optimal value for the parameters, we will actually need to infer the best value for the latent variables, which is going to, for example, be achieved with a maximum a posteriori. So if the direct optimization of sorry, there is someone that is keeping unmuting the microphone. So if you can keep your microphone mute, that would be great. There is I was saying that direct optimization of the log likelihood is often computationally intractable. So we have two paradigms that are often used for this. One is the expectation maximization algorithm, and the other is the variational autoencoders. So in the EM algorithm, we have an alternating optimization procedure that iterates between two steps, an E step that is basically computing the expected completed likelihood, and an M step that is optimizing this auxiliary function with respect to the free parameters theta. This will give a new optimal value for the parameters that we will then use again in the E step. In the variational autoencoder paradigm, we have a slightly different optimization technique. We have a cost function that is composed from a reconstruction term and a regularization term, and then we jointly optimize these two terms with respect to the parameters of the model and of the parameters of the approximate posterior distribution that we have to define. So with this methodological backbone, I will tackle three different tasks. They will all use audiovisual data, and they will be speaker detection, multi-speaker tracking, and speech enhancement. Let's start discussing the first contribution that was published in IEEE TPAMI a few years ago. In this problem, we want to detect people that are both seen and heard at the same time. To do so, we use this robotic head that has a few microphones and a couple of cameras. In our case, we are going to be using only two microphones and one camera, but of course, our method can generalize to other configurations. In particular, we'll be interested in how to measure the relevance of the observations and how to discard those observations that are not relevant. All of this needs to be done, of course, in an unsupervised manner. So to do so, we first project binaural auditory data that you can see here in green into the image plane with a pre-learned model. We also plot the head position in blue. And what you can immediately observe is that while the head position is kind of steady and well concentrated around the true value, the auditory data is kind of spread somewhat, let's say, around the sources, but also there are some samples that are really far away from the speaker's head. This is due to the fact that this pre-learned model is pre-learned for one source, and therefore, when there are two people speaking at the same time, the model doesn't work quite well. So even if the projection doesn't work as optimally as we would like, we need to address the problem of fusing this kind of data. So we are left with a robust clustering task for which there are some methods in the literature, but we are specifically interested in how to model the relevance of each data point. And to do so, we propose to enhance the standard GMM formalism with what we called data weights. So I'll try to give an intuition on how we are going to use the weights and how are we going to define them. If we are in a log likelihood framework and we want a specific data point X to have more weight into the estimation procedure, naturally we would just multiply the log likelihood of this data point by the associated weight W, so that if we want X to have more weight, W will be larger. If we are using a normal distribution as a likelihood, this is equivalent to divide the covariance matrix by this very same weight W. So now we can put this into a Gaussian mixture model formalism, and we will have all the covariance matrices of all the components being divided by this W. But why is this W doing to the Gaussian mixture model? So I plot here an example, a toy example. Of course, it's a two-component Gaussian mixture model, and we are going to be looking at the point in red here. And if we compute the a posteriori distribution of the assignment variable, we can see that for W equals 1, this a posteriori distribution is like 70-30%. If now we use W equals 3, what we are seeing, let's say from the graphical plot, is that the covariance matrices are shrinking, and consequently the responsibilities or the posterior distribution of the assignment variable is polarizing, and it's now 100% 0% or close to that. The opposite effect is observed if we now divide the weight by 3. We can see that the Gaussian distributions are kind of flattening down, and also the a posteriori responsibility is, let's say, unpolarizing, or in a more formal way, it's tending towards a uniform distribution. So we proposed two different versions of this model, one with fixed weights, so those weights are given in advance, and then we can derive an EM algorithm. But the more interesting version is to consider that the weights are latent variables, and we are now led with the task of inferring the weights as well as the parameters of the GMM. We have chosen these weights to follow a gamma distribution simply because it's the conjugate prior of the precision of the Gaussian, and W is playing the precision of the Gaussian in the formulas that I showed in the previous slide. So we need now to derive the corresponding expectation maximization algorithm, keeping in mind that we have now two kinds of latent variables. So my expected complete data log likelihood will need to take the expectation with respect to the joint posterior of the latent variables given the observations and the parameters at the previous iteration. If now we derive this E and M step, we can observe that, of course, we'll have two E steps, one for the assignment variable, which is the EZ step, and one for the weight. So in the EZ step, we will end up with these responsibilities, eta and k, and they are proportional to something that looks really close to a standard GMM. So in standard GMM, you would have the pi k, which is the prior distribution of class k, and then this will be multiplied by a normal distribution. In our case, this will be multiplied by a Pearson type 7 distribution, which is this detail, but it works pretty much in the very same way. Now, if we take a look to the posterior distribution of the weight, this posterior distribution will be conditioned to one of the components of the Gaussian mixture model, and it will be also a gamma distribution because I chose this gamma distribution to be the conjugate prior of the precision. Now, the parameters of this a posteriori distribution, which is a gamma, are two, an and B and K, and we will be highly interested in what's going on in B and K. I would like just to remark that B and K will grow with the Mahalanobis distance between the sample and the cluster K. So the larger this Mahalanobis distance is, the larger B and K is going to be. If we now move to the M step, even if the formulas look quite long, the M step is really close to the M step of a standard Gaussian mixture model. The only difference is this W and K that you can see here in orange. So this W and K is the expected weight, so it's expected value of the weight with respect to the posterior distribution that we just computed in the E step. Now, if we compute this expectation, we reach this division of AN divided at B and K, and we now think back to what B and K was. B and K was growing up with the Mahalanobis distance, so this means that W and K will be actually decreasing when the Mahalanobis distance grows. And now, with this information in mind, we can take a look back to the estimation formula of the mean, which is the second one in the end step. It's mu k star. And we can see that if a sample is far away from all the clusters, then it means that B and K is going to be large for all values of K. So W and K is going to be very low for all values of K. And actually, this sample will have no impact into the estimation of the parameters of the GMM, because all these W and K will be very close to 0 and will have no impact into the sum. So in other words, what we managed to do with this is, if a sample is far away from all the clusters, then it has no impact on the estimation of the parameters, and therefore the estimation of the parameters is robust to samples that are far away or that are really out of distribution. We are just now left with the task of initializing the gamma distribution, or setting the prior values of the gamma distribution. And we do that once again from the observation and the understanding of the problem. So if we take a look again to this image, we can see that we are mostly interested in the, for instance, in the audio samples that are close to visual samples. And in the same way, we are interested in visual samples that are close to audio samples. And we are interested in doing so because, as I said at the beginning, we want to detect people that are both seen and heard at the same time. So basically, we use a Gaussian kernel to initialize the parameters of the gamma distribution with this intuition. We have evaluated our method in a bunch of clustering data sets, but I'm here presenting the results on the particular task of audiovisual speaker detection. We have used the HDR dataset that is freely accessible at our webpage. And in particular, we are collecting observations, audio and visual observations, over windows of 400 milliseconds. And this means that we are left with a robust clustering problem that has only 60 observations. So this is a very few amount of data to perform clustering. We have evaluated this in 3 kinds of scenarios, which have increasing number of people and increasing complexity. And we have compared our weighted data GMM with a GMM plus a uniform component, which is supposed to absorb these outliers, so to be robust to a certain extent, and also with a mixture of T distributions that are heavy tail distribution, and therefore supposed, again, to be robust to outliers. We can see, in the results that the amount of correct detections, of course, decreases when the complexity of the scenario increases, but also that when we compare the weighted data GMM, except for in the easiest scenario, it outperforms the other methods. And in the easy scenario, it does not, because it gets maximum performance as well as the GMM with a uniform component. You can see here a video that is showing the results. So on the left, you have the observations and the ground truth of the active speaker that is shown in yellow. And on the right, you can see the results. So I recall that we are analyzing this of using windows of 400 milliseconds. So therefore, here there is no collection, or there is no understanding of the evolution over time of these estimations, right? This is done independently every 400 milliseconds. So this is very challenging, because when people, cross or occlude each other, since we have no understanding or knowledge on what happened before, it's very difficult to make a difference between 2 people occluding each other that basically produce observations that come from the same direction, or just 1 person standing in this position. So this is why we addressed a second contribution that was also published in IEEE PAMI last year on audiovisual speaker tracking. So here, of course, the aim is to accumulate this information over time and use the previous information to have a better estimate of the present position of the speakers. And in particular, we would like to be able to track with audio only, video only, or audiovisual data. So in this sense, it changes a bit the philosophy of the previous contribution in which we were looking for people that were both seen and heard at the same time. So there are, of course, a bunch of methods, many methods to do multiple object tracking using visual observations. When it comes to audiovisual tracking of multiple objects, then there are far less works. And in particular, there are works using particle filters and probability hypothesis density. The limitation of the way these two frameworks are used for audiovisual tracking is that they require an almost continuous flow of auditory and visual observations, and this is not quite fit for the kind of scenarios that we want to address. Because in natural conversations, people take turns when they speak, and if the robot is looking to one of the persons, as in the case in the image, the other person will likely be outside of the field of view. So to model this, we assume that we are going to be tracking n people over time, and the position or the bounding box, the hidden state, is going to be denoted by y. At every time step, we will have a bunch of observations, let's say k observations, that are going to be bounding boxes and binaural localization cues. And therefore, because we don't know which of the answers produce each of the k observations, we need an assignment variable that is inferring which bounding box and which binaural cue has to be assigned to each of the persons n. So here, as in the previous case, we are left with two kind of latent distributions: the position over time, which is this y, and the assignment variable that is denoted by z. We decided to model this with linear Gaussian dependencies, meaning that both the model for the dynamics of the hidden variable y is going to be a Gaussian, centered at the previous time step, and the observations that are produced by a source is also going to be following a Gaussian distribution. So if we take this and we put all this together, an attempt to compute the posterior distribution of one position of one person at time t, even if we can analytically write down this distribution, we end up with a Gaussian mixture model that has way too many components to be a working solution. So even if we have an analytic solution to this, computationally, this is untractable. So we are going to address this issue from the following two remarks. First, if, and this is of course hypothetical, if we knew the positions, then the only thing that we need to do is to assign the observations to these positions. And this is equivalent to say that I'm going to run the step of a GMM at each time frame. And we know how to do this, and this is quite efficient. The second remark is kind of dual to the previous one. If we now assume that we know the assignments ZTK, then we can create a virtual observation for each source at every time step, and therefore the tracking problem boils down to running n Kalman filters in parallel. So from these two remarks, what we are going to do now is impose this factorization of the posterior distribution. This is our variational approximation, and we are now imposing that a posteriori the variables y, which are the hidden positions of the persons, and the variable z are going to be independent a posteriori. Now, if we do so, we effectively find our intuition that we described here is because we are going to be alternating between a GMM at each time step and a Kalman filter per each source. And if I write down how the mean of the Kalman filter is updated, we can see that it has three contributions. The last one is the one from the past that accumulates all the past information. And then we have two contributions, one here in green with audio and one here in blue from the video. Now, importantly, these two sums that you have here have these alpha coefficients that are the responsibilities that are computed in the GMM-like step. So therefore, if at a certain time step, all the green alphas are 0, this means that I cannot use audio to track this source. I can use only video. The dual is true, of course. If all the blue alphas are 0, I'm going to be using only audio. But if none of them is 0, then I will be using audio and video to track the source at this time step. Very importantly, this is completely unsupervised because it comes from the GMM-like E step. So with this, we managed to effectively be able to use either audio or video or audio and video to track the many speakers. We have evaluated this using the AVDR dataset. And we can see here that our two proposals that are basically the visual variation OLE-M and the previous work that was using only video are effectively outperforming the strategies based in particle filter and the probability hypothesis density filter. And this is due to the fact that we accept, I mean, we are very, our method is very flexible and we don't need a continuous flow of audiovisual information for every source to be able to track the sources. If now we focus and we compare the audio and video, so if we take a look to this full column, so full column means that we have visual observations everywhere in the image, we can see that audio doesn't bring much into the equation. This is normal because if we have a head detector or an upper body pose detector, well, this is quite precise compared to the auditory localization. But we also tried in a different setting in which the blue parts in the image are supposed to be blind, and we are not going to be having visual observations in these two regions. And in that case, we can see that audio can actually bring some interesting improvement for the tracking. So you can see here a video. On the upper left part of the video, you have the output of our tracking method. On the upper right is this visual contribution, so the blue part in the equation that I showed before. The green part is, the bottom left part is the green part of the formula that I showed before. This is the audio contribution. And finally, you can see the contribution from the past in the bottom right. So what you can very easily observe, and this is pretty obvious from the images, is that the visual contribution is pretty steady if people are inside of the field of view. However, when people are outside of the field of view, there is no way we can track with video, and audio can provide some interesting cues. However, audio in general is much less precise, and this is why if we have vision in terms of localization, it is much more reliable. What we cannot do, however, with vision is to assess if the person is speaking or not. So this is, I'm not going to present results about this, but this is something that we could address also with this method. This means audiovisual source diarization. We have produced a robotic implementation of this tracker. In here, apart from being able to run this on a robotic platform, we should, in terms of complexity, I mean, we needed also to take into account the fact that the robot was moving. In here, it was supposed to be tracking, I mean, looking permanently at this, at Yutong, which is the person with the black t-shirt. And what you can see here is that when the robot moves, there is this pink arrow that appears, and that this is the impact of the rod motion on the relative movement of the bounding box in the image plane. To make things much more concrete and easy, when the robot turns to the left, the bounding box is going to move to the right, and therefore you will have a pink arrow to the right. This is actually compensating for the ego motion of the robot and provides much better tracking results than if we don't take the robot's motion into account. The third contribution that I would like to discuss is on audiovisual speech enhancement, and was published this year at IEEE ASLP, and the second version, I will present both, is under review at IEEE Transactions on Signal Processing. So the task of audiovisual speech enhancement is the one of extracting clean speech from a noisy mixture, and a set of visual cues. In our case, we are going to be using the part of the image that is related to the lip region of the speaker's face. There has been a bunch of literature on audiovisual speech enhancement on, let's say, supervised settings, and they attempt either at estimating a time frequency mask or directly inferring the clean spectrogram. There has also been some works proposing deep generative models for audio-only and supervised speech enhancement. So the difference between supervised and unsupervised is going to become clear in the next slide. So we will be addressing audiovisual and supervised speech enhancement, and in particular, we would like to understand how to optimally fuse auditory and visual information. So supervised audiovisual speech enhancement is the task of cleaning some noisy speech signal with the help of visual information. So here you can see that the input to this network is noisy speech plus a set of visual frames, while the output is directly the clean or enhanced speech. This means implicitly that the network is learning to denoise, and therefore it's depending on the noise types that the network has seen during training. And we don't know how this is going to generalize to other noise types. In unsupervised audiovisual speech enhancement, we are training a model with clean data. So the training happens only with clean data. And then at test time, we are left with a double task of inferring the noise distribution and at the same time cleaning the noisy speech signal. We will compare our proposals to two, let's say, very standard methods. The first one being audio-only variational autoencoder. So this is a standard reconstruction task. And the second one is video-only variational autoencoder, whose input are the lip images and the output is the clean speech. Our first proposal was to concatenate vision everywhere in the prior, in the decoder, and therefore in the encoder as well. So this is what you can see in the figure. And we tried first to train this, let's say, in a very straightforward manner, but the problem is that the network is not forced to learn from the vision. So we decided to add this extra term that you can see here in orange to force the network to give some representation power to the prior visual distribution. So at test time, we add this non-negative matrix factorization model with a complex normal distribution. We have an MCM algorithm to estimate the optimal values of the non-negative matrices W and H. And in order to clean the speech signal, once the optimal W and H are obtained, we are using an expected Wiener filter. So the Wiener filter is, you can see here inside of the expectation, and the numerator is the energy of the sound source, and the denominator is this energy plus the energy of the noise. So you have to understand this in the following way. If the energy of the clean source is much higher than the noise, this coefficient is going to be close to 1, and we will use the input as the estimate of the clean speech, and otherwise we would rather have this estimate to be close to 0. Because this energy depends on the latent code Z, we have to take the expectation over Z. We evaluated this using the NTCD-TMID dataset, which you can see here the results on 3 different metrics. This depicts the improvement on the metric. So this is why for good noise conditions, towards the end of the curves is also going down, because it's very difficult to improve something that is already very good. And the main conclusion here is that the audiovisual fusion strategy is superior to the best of the audio and the visual, of the audio only and the vision only most of the times. The problem of this architecture is that it's systematically fusing audio and video. So we propose an alternative, which is combining a mixture model with a nonlinear decoder. And we are now assuming that the prior distribution of the latent code can come either from an audio prior in green or a blue prior or a video prior in blue. Now, of course, due to the nonlinearity, the posterior is going to be intractable, and now the posterior is going to be a joint posterior of the latent code and the mixing variable, because we don't have this mixing variable, it's unsupervised, and we will have to split this into two distributions. For coherence with the prior, the posterior, the encoder is going to be considered to be also a mixture, and this is why we named this architecture mixture of inference networks variational autoencoder. So the problem now is how to train this architecture. So if we start from the log likelihood and assume the factorization that I showed a couple of slides before, and after some tedious derivations that I'm not showing here, we end up with this variational lower bound that consists on two terms that are more like EM-like and two other terms that are more VA-like. So the first two terms regard the posterior distribution of the mixing variable, so R alpha n, and of course the M step associated to this variable. So once I run the E alpha step and I obtain the a posterior distribution, I can go back to the second line and understand that this is nothing like a VA cost that now has to be averaged over the mixing variable alpha n. So just to give some understanding on what this posterior distribution over the alpha n looks like, it's of course a Bernoulli distribution, and the parameter of this Bernoulli distribution depends on the prior, obviously, but also on the ability, on the relative ability of the variational autoencoder to reconstruct the nth spectrogram vector using audio compared to using video. So if this relative ability is much higher in, like its positive number, then Pn is going to be close to 1, because a posteriori we understand that we need to reconstruct this with audio, and the dual is also true. I don't detail here what we need to do for speech enhancement, but we will end up with another version of the Vinol filter averaged over, of course, the posterior distributions. So when we run experiments on the very same data set, here to test the ability to be robust to noise in audio and video, we added noise to both auditory and visual samples to 1/3 of the input frames. And then we compared various versions. What we are interested in is taking a look to the green curve, which was our original intuition, and we can see that this is superior or at least equal to all other strategies for most of the cases. So including the turquoise curve, which is the systematic concatenation of auditory and visual information, which was our first proposal. So to start concluding, I have described here how to use probabilistic models for 3 audiovisual tasks, namely speaker detection, where we have proposed a weighted data GMM formulation, speaker tracking, where we have proposed a variation EM algorithm that is able to use either audio or visual or audiovisual information for source tracking, and finally, 2 VA-based strategies that account for lip information. And these 2 strategies, let's say, in terms of fusion philosophy, the first one corresponds more to the audiovisual speaker detection, and we were systematically using both auditory and visual data. And the second strategy is actually finding the optimal combination, so it corresponds more, let's say, once again, in fusion philosophy, into the audiovisual speaker tracking algorithm. However, these methods have limitations when we start thinking and we start wondering how will this work in a real scenario. The first limitation regards the first 2 contributions and is due to the fact that the auditory to visual mapping is it's modeling and exploiting the variation pattern. It's learned for one source. It depends both on the room and on the robotic platform. And it varies, of course, with the position of people, otherwise we couldn't exploit it for localization, but also it changes with the position of the robot. So now, how to exploit this when there are multiple moving speakers, that the robot is also moving, that it may change from one room to another, that the reverberation pattern changes. I mean, this is a really challenging and very general problem. So on the audiovisual speech enhancement part, we have basically learned to reject bad lip images and to exploit clean frontal lip images. And we do so without any consideration on what was happened before. So if you think about it, if someone is at some point is covering the mouth while speaking, of course, for a few frames, this is going to be the case. So it makes sense to have some temporal model over there. So in this regard, we have just published a preprint on temporal models that are based on variational autoencoders. We made the strong pedagogical effort to put this together and to produce a nice and comprehensive preprint that you can download from arXiv. And we call this class of models dynamical variational autoencoders. So beyond that, there are many interesting things to do. But we would specifically like to, of course, overcome these limitations and to end up with a method that could actually allow for joint tracking and separation of multiple speakers with a robotic platform that is moving and walking around. We would also like to account for the group dynamics. This could be useful as a prior for tracking, for diarization, for separation, and for many of the, let's say, downstream tasks. And we would also like to start thinking on how to make the robot be versatile enough to adapt reverberation patterns, and why not other kind of patterns of environments that have not seen or not been heard before. On top of this, and this is a challenge that is common to the scenario, and of course to all the three previous items, we need to tackle this with the data scarcity that is associated to multi-person interactions in the wild. We also need to start taking into account the robot actions and to use them. So we would like to use the robot to approach a person, a group. We need to learn the optimal policies so that the robot behaves correctly while chatting with people, and also that is able to enhance its own perception, meaning improving the quality of the speech signals or increase the pose recognition accuracy of a group of people that are interacting. So I would like to show you some preliminary results on robot actions. This is a simulation, of course, because we don't have access to the lab yet, and we will soon hopefully be able to do this with a real robot. In here, you can see a robot that is supposed to join a group of people, and in particular, to end up looking at one of the persons within this group. The interesting part here is not only the fact that the robot is able to take into account people as regions in which the robot should not step in. This is good for safety, but also, and you can see here in the white blob in the middle, the robot is considering the center of the group as a region in which it should not step. And this is very important because otherwise it would be socially very awkward that the robot steps in the middle of the group to address one of the persons of it. We have many challenges in the future. A very long-term challenge is to have a computational paradigm that actually spans from theory to practice, and that we can make consistent progress in social intelligent robots. The theoretical formalization would, of course, require also expertise in social sciences. So I hope we can partner up with top researchers in this area. From that, we will be able to derive models that are able to learn social skills, to collect data sets or simulate data, because some of the data would need to be simulated so as to train these models. And finally, to derive proper evaluation metrics and experimental protocols to measure this progress in robotic social intelligence. We have the means to address part of these issues. Of course, not all of them. The main funding research is the H2020 Spring project that I am coordinating. It's 8 partners all across Europe, and it's equivalent to have 20 full-time persons over the span of the project. I was also awarded with a project from the French funding agency within the Young Researchers program. And finally, together with Radu, we are co-chairing the team in audiovisual machine perception and interaction for robots from the Multidisciplinary Institute of Artificial Intelligence. So thank you all for attending and listening, but especially to the committee members for the work and the effort that they have put into that. I'll be gladly taking your questions and comments.
Okay, so Xavier, the committee found the presentation very clear and very pedagogical. So you have demonstrated a impressive expertise in the very innovative field of visual audio combined analysis. The presentation also demonstrated strong skills and strong concern on principled mathematical formalism. So the jury appreciated that. And so the answer you made to the numerous and sometimes difficult questions from the committee showed a considerable knowledge in your research domain and demonstrated as well a clear vision on the future of the field and about your own agenda about this future. So for your current and past supervisions, your scientific perspectives and the numerous important results you obtained with your students, the committee unanimously decided to give you the habilitation à diriger des recherches from the University of Grenoble-Alpes. So congratulations, Xavier.
Thank you, Edmond, and thank you to the committee for this decision. Yes, we can try to clap remotely.
Congratulations, Xavi. Bravo.
Congrats, Xavi. Excellent work.
Thank you, Christian. Thank you, Emmanuel.
Congrats.
Congrats.
So where is the champagne, Xavier?
It's in the fridge. Actually, Rita will be happy. It's Prosecco.
No, I would prefer a champagne. Come on.
You will have it next. You will have it next time we can gather.
Okay,
together.
Xavi, you know my address, so I can wait to home gift a good champagne from your area.
You accept deliveries, huh? Okay. Thank you, guys. So I know you are. I mean, it was really long for everyone. I just have 3 slides because I would like to thank people that really contributed to this. So if we can just spend 2 minutes. I'd like, of course, to thank all the attendees for the time. It was pretty long. We had many interesting and constructive questions from the committee members, for which I thank them. And I would like you to know that I will be very happy to discuss about all of these things in the future when we can gather and we can have lunch or dinner all together. I will be really happy to do that. I would also like to thank you all the scientific, technical and administrative colleagues that contributed to many different levels to what I have presented today and to what I submitted as a thesis and the work we are doing every day. So in particular, I would like to thank my PhD and postdoc mentors, Radu and Nico. They taught me what is to be a researcher and what things are interesting to do and how to choose, how to make choices in my research career. They started as mentors and they became colleagues, just like many other people that with whom I have contributed into the past, and some of them we keep on working, and maybe Some of them we stopped doing things together, but we will happily retake the work together in the future. I would specifically like to thank the team, the excellent team that we have in the perception here at INRIA in the perception lab. I feel honored to be able to work with them. They challenge me every day, more or less like the committee members did today with the questions. So they challenge me with new ideas, new problems, and with new solutions. So I am very happy to be working with them. And finally, I will of course like to thank my family, my parents, my brother and his family, and Julie.